Okay, so welcome back to another video. So this time we are actually given two sequences, a sub I 0 equals 1 divided by 2 raised to I minus 1, and then a sub I j plus 1 is equal to a sub I j squared plus 2 times a sub I j. So now the question we're being asked is to find the limit as n approaches infinity of a sub n. So this is pretty much going to be the first time calculating the limit of sequences, so this is going to be very interesting. So, okay, first step, let's actually rewrite our given, so a sub I j plus 1 in particular. J plus 1 equals, and what I'm going to do here is I'm actually going to add and subtract 1 plus 2 aij plus 1 minus 1, and then notice that the first three terms here, they actually form it forms a perfect square, so we can unfold it and get the following: aij plus 1 square minus 1. So far so good. Now next we want to do is let's actually find a pattern, and when I say find a pattern, eventually we can actually find a formula to help generalize the sequence on and observing the behavior. So really let's keep the index I fixed, and then start with j is equal to 0 and then all the way up to infinity until we actually discover a pattern here. So let's actually start with j is equal to 0, so in this case we get 0 plus 1, so this is a sub I comma 1, and so this is equal to a sub I comma 0 plus 1 square minus 1. Okay. Now a sub I minus or comma 2 equals a sub I 1 plus 1 square minus 1, which we can write this as let's see, that's a sub I 0 plus 1 square minus 1 plus 1 square, and then minus 1. And so that way we get, I have to use the chair for this. Oops, almost fell. So that means we get a sub I comma 0 plus 1 raised to the 4th, since minus 1 plus 1 cancels, so the square, the power 2 just distributes to here, then minus 1. Okay. Now let's calculate a sub I comma 3 equal to a sub I then 2 plus 1 square minus 1, which then that's equal to, so we have this, so let's just substitute. So a sub I comma 0 plus 1, 4 minus 1, then plus 1 square minus 1. And just like before, minus 1 plus 1 cancels, then we just distribute the power 2 into here, so we get 8 to the power 8. So a sub I 0 plus 1, 8 minus 1. And now let's just keep going so forth. So when we now the general formula for this a sub I comma j is actually just a sub I 0 and plus 1, then it's raised to the 2 raised to the j minus 1. Okay, so let me underline this in black, that we have our general formula for a sub I to j. So this is our general formula here, like so. Okay, nice. Okay, so now that we have this, we're given that a sub I comma 0 is 1 divided by 2I minus 1. So let me just write it over here. 0 equals 1 minus 1 divided by 2I minus 1. That's our this is our given. Okay. So let's actually rewrite this term. So this is also known as 1 divided by 2i, and then raised to the 2 minus 1, which that can be written as 2 divided by 2i. And so now that we have a sub I sub 0, we can actually just plug this into our term here. So a sub I comma j is equal to, it's commutative, so I'm going to move the 1 in the front. So this is 1 plus 2 divided by 2i raised to the 2j, then minus 1. Okay, nice. So now, and I'll underline this in black again for the second time since we just plug in our given. Okay, cool. Now the last thing we're actually going to do is now we're going to calculate what we're being asked to find the limit as n approaches infinity if a sub n sub n. So we're going to find the limit of this sequence. Okay, so the limit as n approaches infinity of a sub n comma n. Okay, now that means I is equal to n and j is equal to n, so that means substitute all our i's and j's of the index with a new index for n. So 1 plus 2 divided by 2n, then raised to the 2 raised to the n minus 1. Okay, so now we're actually, let's actually do some substitution. So we're gonna let t equals 2 divided by 2n, okay? And now let's actually fix this a little bit. So this means I can just multiply the 2n to the other side, so that means, and then divide by t, so we have 2n is equal to 2 divided by t. Okay, so then that would have to mean that the limit as n approaches infinity of f, some function f for evaluated at 2n, so that would have to equal the limit as t approaches 0 of it's supposed to be f here, f of 2t. Okay, so now we have that. Let's actually make our substitution. So we have the limit now with t approaches 0. Okay, so f 1 plus let's see, that's supposed to be t, so t's over here, and then 2 divided by t right here. Yeah, there we go. Okay, and then minus 1, of course. Now I can actually factor out the 2 here, and then we're gonna get some new exponents. So the limit as t approaches 0 of 1 plus t raised to the 1 over t. Here, you can't see that t, so let me actually write it like this. 1 then t. Okay, then square, then minus 1. Okay, so now remember, I've actually discussed this a couple times in the past video, but if you look at the inside of our function, this is actually the standard formula for Euler's constant. When you're taking, it's also another way of writing Euler's constants. There's one where t approaches 0 and then t approaches infinity, but that's also written differently. But since we're given t's approaches 0, so the formulation for 1 plus t raised to the 1 over t, you take that limit as t approaches 0 is going to equal e, Euler's constant. Okay, so use it with that definition, so that means this is e square. Well, I'm not going to need the parentheses for this, and then e, then distribute the square, so it's e square minus 1. Okay, so therefore we have actually found our answer, and let me write the conclusion again one more time. Therefore, triple triangle dots like so, the limit of as n approaches infinity of a sub n comma n is equal to e squared minus 1. Like so. Cool. That's pretty cool limit for sequences, right?